Propositional logic, part 6, equivalent, contradictory, consistent, and inconsistent statements. We're going to look at the concept of logical equivalence first. Logically equivalent propositions are ones that have identical truth tables, where they have the same truth value under their main operator for every row of a truth table. So here's some examples in ordinary language. It's not the case that both Marvel movies are good and DC movies are good. Either Marvel movies are not good or DC movies are not good. So if you heard these, you might not be able to tell right away that they're actually logically equivalent statements, but you can prove that using a truth table. So you have a truth table set up on the right. There's two simple statements, which here we're calling P and Q. You'll notice the first ordinary language statement is a negation. You're saying it's false that it's not the case that both Marvel movies and DC movies are good. So that's going to be a negated conjunction, which you can see in the third column in that table. And in the fourth column, we have our other compound statement, which is a disjunction of negations. You're saying either Marvel movies are not good or DC movies are not good. So let's start with the first compound proposition, filling in its truth values. So you'll notice we have to start with the dot first. It has the smaller scope. The scope of the dot is bounded by those parentheses. The rule for the dot is it's only true when both of its conjuncts are true, which only happens on row 1. Then the negation negates the entire conjunction. So this is just going to reverse or flip the truth value of the dot on each row of the table. And I've put in bold the truth values of the main operator of that compound proposition. Now let's put in the truth values for the second compound proposition. This is a disjunction of negations. The negations have smaller scope, so we start with those. We have tilde P and tilde Q. So we just reverse or flip the truth value of P on each row to get the value of tilde P, and the same thing for tilde Q. And then the rule for the disjunction is it's only false when both disjuncts are false, which you can see only happens on row 1. But if you look at the bolded truth values of those compound propositions, you'll notice they're the same on every row of the truth table. So that means they are logically equivalent propositions. Now let's look at the concept of contradictory statements or propositions. Two statements that have opposite truth values under the main operator on every line of their truth tables are contradictory. So here's a couple of ordinary language examples. You're not from Pasadena, or you are from Los Angeles. Another one. You are from Pasadena and you're not from Los Angeles. Once again, you might not be able to tell just by listening to these what their logical status is with regards to each other. But if you do the truth table, you can prove that they are in fact contradictory statements. So let's start with putting the truth values under the first of those compound propositions. The tilde has the smaller scope. It only negates the P. So for each row, we reverse the truth value of the P to calculate the truth value of tilde P. Then we go to the wedge, which is the main operator. The wedge is only going to be false where both disjuncts are false. You can see that on row 2, where tilde P is false and also Q, the other disjunct, is false. Now let's look at the truth values for the second of those compound statements. The tilde has the smaller scope. It only negates the Q, so it reverses the truth value of Q on each row of the table. The dot, its rule is that it's only true where both conjuncts are true. That only happens on row 2, where tilde Q is true and also P is true. You'll notice the truth values of those two compound statements are the opposite on each row of the truth table. So that's what makes them contradictory statements. Consistent statements are ones where there's at least one line of their respective truth tables where they're both true. So that means it's possible, logically speaking, for both of them to be true, and that's what we mean by consistent. Here's a couple of ordinary language examples. The Dodgers will win the World Series, or the Packers will win the Super Bowl. And the Dodgers will win the World Series, or the Packers will not win the Super Bowl. Are those logically consistent statements? So to prove that they are, we have to do the truth table. So let's start with putting the truth values under the first of those compound statements. The rule for the wedge is that it's only false where both disjuncts are false. You can see Both P and Q are false only on row 4. So now let's do the second compound statement. We start with the tilde, which is the operator with the smaller scope. It only negates the Q. So that reverses the truth value of Q on each row. The rule for the wedge is that it's only false where both disjuncts are false. You can see on row 3, P is false, and the other disjunct tilde Q is also false. Otherwise, it's going to be true. And even though they don't have the same truth values on each row, so they're not equivalent, they do have 2 rows where they're both true, rows 1 and 2. So that makes them consistent statements. Also, you'll notice because the truth values are not the opposite on every row, they're not contradictory. So they're not equivalent, they're not contradictory, but they are consistent. And then finally, let's look at the definition of inconsistent statements. These are statements that do not have any line of their respective truth tables where both of them are true. So there's always going to be at least one of them false or both false on every row of their respective truth tables. So let's look at a pair of ordinary language examples. You're going to Disneyland and you're not going to Universal, and you're going to Disneyland if and only if you're going to Universal. So the translation of the first one of those ordinary language statements is P dot tilde Q. So we have a conjunction, a dot, where one of the conjuncts, the second one, is a negation. It has a tilde. You're not going to Universal. The next ordinary language statement has the phrase if and only if, which is an indicator for the triple bar or the biconditional. So let's fill in the truth table for the first of those compound statements, P dot tilde Q. The tilde has the narrower scope. It only negates the Q, so we just reverse the truth value of Q on each row. And then to calculate the truth value of the dot, we remember once again that the dot is only true where both of its conjuncts are true. That only happens on row 2, where P is true and tilde Q is true. Now moving to the triple bar, it is true in those cases where both of the propositions it links have the same truth value. Otherwise, it's false. So you'll notice on rows 1 and 4, both of the propositions or both of the statements P and Q have the same truth value. That makes the triple bar true. Otherwise, when they have different truth values, it's false. You'll notice these are not equivalent because they don't have the same truth value on every row. They're not logically contradictory either because they don't have opposite truth values on every row. However, they're not consistent because there's no row where both of those statements are true. So that's what makes them inconsistent. There's always at least one of them false on any row of the truth table. On row 1, the first compound proposition is false. On row 2, the second one is false. On row 3, they're both false. And on row 4, the first one is false again. So because there's no row where both of them are true, they count as inconsistent statements. Before we move on to some sample problems, let's look at some questions for discussion that will help clarify the relation between the concepts we just learned. First, a couple of questions about equivalent statements. Can equivalent statements be consistent? The answer is yes. Equivalent statements have the same truth value on every row of their truth tables. So if one of them has a truth value of t, the other one will also have a truth value of t on the same row, which would make them consistent. Can equivalent statements be inconsistent? You might think the answer is no, but the answer is actually yes. Can you figure out why? The only way equivalent statements can be inconsistent is if they're both self-contradictions. So if they're false on every row of the truth table, that would make them equivalent, but technically they also would be inconsistent because there's no row on which both of them are true. Now let's look at some questions about contradictory statements. Can contradictory statements be consistent? The answer is no, because they always have opposite truth values. If one of them is true, the other one has to be false, which means there's going to be no row of the truth table where both of them are true. Can contradictory statements be inconsistent? The answer is yes. In fact, all contradictory statements are also inconsistent because their truth values are never going to agree. There's always at least one of them that's going to be false. So let's look at a sample problem. We're given 2 compound propositions, and we have to identify whether they're equivalent, contradictory, consistent, or inconsistent. So we have two simple propositions within those compound propositions. P horseshoe Q has the simple propositions P and Q, and tilde Q horseshoe tilde P also has the same simple propositions. So our truth table is going to have 4 rows because we have two simple propositions, P and Q. So we've arranged the truth values for those simple propositions on those 4 rows. Now let's calculate the truth values of both of our compound propositions, P horseshoe Q and tilde Q horseshoe tilde P. So you notice with P horseshoe Q, there's only one logical operator, so we only have one calculation to do. The rule for the horseshoe is that it's only false where the antecedent is true and the consequent is false. You can see that on row 2 because the antecedent P is true and the consequent Q is false. The other compound proposition has more operators, so we start with the tildes that have the smallest scope. In this case, they're only negating the simple propositions. We reverse the truth values of a simple proposition Q on each row to calculate tilde Q. We reverse the truth value of the simple proposition P on each row to calculate tilde P. And then we remember that the horseshoe, its rule is that it's only false where it has a true antecedent and a false consequent. You can see that on row 2. So now that we've calculated the truth values of these compound propositions, we ask ourselves, are they equivalent, contradictory, consistent, or inconsistent? The answer is they are equivalent because they have the same truth value on each row of the truth table. That is a very strict definition to meet. So to make sure that they're equivalent, we have to check each row to make sure that they are actually the same on each row. So a second sample problem, a new set of compound propositions, C dot D and tilde C wedge tilde D. Once again, we have two simple propositions, C and D, so our truth table is going to have 4 rows. Now let's calculate the truth values of those compound propositions. So with C dot D, it's a conjunction. The conjunction is only true when both of its conjuncts are true, which you can see on row 1. The disjunction is only false where both of the disjuncts are false. You can see that on row 1 as well. So are these propositions equivalent, contradictory, consistent, or inconsistent? They're not equivalent because they don't have the same truth value on every row. So now let's check to see if they're contradictory. They are indeed. If you look at every row of the truth table, they have opposite truth values. So that means that they are contradictory propositions. Let's look at a third sample problem. We have two new compound propositions, T triple bar U and T wedge U. So once again, we have two simple propositions, T and U. Our truth table is going to have 4 rows. Let's calculate the truth values of those compound propositions. So these are, there's only one logical operator in each of these compound propositions, so we can just basically apply the rule for those operators. The biconditional is going to be true on lines 1 and 4, where both of the simple propositions are true, otherwise it's false. And the wedge is only going to be false where both of the disjuncts are false on line 4. So are these equivalent, contradictory, consistent, or inconsistent? The answer is consistent. They're not equivalent because they don't have the same truth value on every row. They do on row 1, but not on rows 2, 3, and 4. They're not contradictory because they don't have opposite truth values on every row. You'll notice row 1, they do have the same truth values. So the answer is consistent because row 1 is where they're both true. There's at least one row of the truth table where both of them are true. Finally, another pair of compound propositions, tilde A dot B and tilde B dot A. Are these equivalent, contradictory, consistent, or inconsistent? So we have two simple statements once again, so our truth table will have 4 rows. Let's fill in the truth values under our compound propositions. Filling in the truth table, we see that each of those conjunctions is only going to be true on one row of the truth table. So for each of them, there's one row where both of the conjuncts are true. You can see on row 3, the proposition tilde A dot B has the first conjunct, tilde A, is true, and the second conjunct B is also true on that line, making the whole conjunction true. On every other line, at least one of them is false, so the conjunction is false. The second proposition, tilde b dot a, is only true on row 2, because on row 2, tilde b is true, and also a is true. So what does that make these propositions? Are they equivalent, contradictory, consistent, or inconsistent? They're not equivalent because they have different truth values on rows 2 and 3. They're not contradictory either, however, because on rows 1 and 4, both of the propositions are false. That makes these propositions inconsistent because there are no rows on which both of them are true, but there are 2 rows on which both of them are false. So that's rows 1 and 4. Because they're neither equivalent nor contradictory, nor are they consistent, lacking any row where they're both true, that means they must be inconsistent.